Last time we talked about Fermat's theorem, which states that if a function has a minimum or a maximum, then it must have either a zero derivative or a non-existent derivative at that point. And we also talked about the extreme value theorem, which is a guarantee that maxima and minima exist. Now, in particular, if you have a continuous function on a closed interval, the closed interval part is very important, then the extreme value theorem guarantees you must have an absolute minimum and maximum on that interval. You could have two of them with the same value, but they must be there. Now, one of our ultimate goals in Chapter 4 is to use the tools of calculus to help us find locations of minima and maxima. Now, it seems like from the above here that finding where f prime is equal to 0 is going to be useful. So the idea today is, are there any conditions on a function that will guarantee that the derivative will be 0 somewhere on, this time we'll call it an open interval. So we are looking for guarantees, strong statements. Now, before I state this result, I want to try to walk through and think about the conditions here. So what do we need? If we want f prime equal to 0 somewhere on AB, then it seems to make sense that we should require that f prime should exist on AB. Right? I don't want to have to necessarily worry about pokey things, corners, that type of stuff. So as a starting point, let's say that we want f prime to exist on this open interval AB, which implies that the original function we're dealing with has to be differentiable on AB. Now, we automatically get, from differentiability, we automatically get continuity on the same open interval. So that's pretty good. If we want to restrict ourselves here, assuming that our function is differentiable everywhere on an interval gets us that our function is going to be continuous everywhere. So the one thing that we do need to start with is that our function we will assume is differentiable. Now, if I go one little step further in terms of an assumption, I would love to be able to bring in the extreme value theorem somehow. I would love to guarantee that I have minima and maxima. I think that will be very useful. So I am going to take this one result and I'm going to bump it up a bit. In order for the extreme value theorem to hold, the function has to be continuous not on an open interval, but on a closed interval. So I'm going to make an additional assumption. I am going to not only assume that my function is differentiable, I am going to assume that my function is continuous on a closed interval AB. And that means we get the extreme value theorem, and I'll put it in air quotes, for free here, which is nice because you never know what use it'll give you. And in fact, it's going to be very important for us here. So if our function is continuous on a closed interval AB and differentiable on an open interval AB, is this enough for f prime to equal 0 somewhere on AB? Now, normally I'd like to get you to sit and think about it, but you could pause the video and stop and think. And I'm hoping that at some point you can come up with what's called a counter example, an additional example to show you that no, this is not going to be enough. And here's a very simple example. Take a function that's linear on the interval AB. It doesn't really matter if it has a positive slope or a negative slope. This function is certainly continuous on this interval. So f is certainly continuous on AB. There are no holes, no gaps, no jumps, no breaks. It is certainly differentiable on the open interval. No pokey things. No vertical asymptotes. No vertical tangent lines. Any of that. But f prime is always greater than 0 on this entire open interval. So that isn't going to work. Those two conditions are not enough. Now, if they're not enough, what else do I need? Right? What other condition will do the job? So from this picture above, this seems to be our counterexample. So let's try to figure out from this picture above what else I could do. And I think that the easiest thing here is to imagine that you could grab this linear function with your hands. Grab one endpoint, your left endpoint in your left hand, the right endpoint in your right hand, and say to yourself, okay, this thing has a positive slope. How could I make this slope 0? And I think if you visualize it like this, you could see that if you forced those endpoints to be at the same height, then it would have a 0 slope. So if you forced f of a to be f of b, then I think you can see from the picture that this function would just be horizontal. And in this case, f prime would be 0 everywhere on that interval. And so this is the idea. We've got a set of conditions that will guarantee that we have a 0 derivative. So this is something called Rolle's theorem. If your function is continuous on closed interval AB, if it's differentiable on open interval AB, and f of a equals f of b, then there exists a point C somewhere between a and b, so that f prime of c equals 0. So Rolle's theorem has 3 conditions. And when you get those conditions satisfied, there's a conclusion. And the conclusion says that, look, if you meet those 3 conditions, I will give you this outcome, that you must have a 0 derivative. Well, why? How do these conditions work, right? If your function is continuous on the interval a to b, the extreme value theorem says you must have an absolute min or max. Okay? And you must have it on the closed interval AB. All right. If your minimum or maximum is somewhere in the interior, so between A and B, that means Fermat tells you that at a max or a min, either the derivative is 0 or the derivative doesn't exist. But we got rid of this because we said that f is differentiable on the open interval. So we must have a 0 derivative. If the minimum or maximum are at the endpoints, A or B, then that third condition will guarantee what we have. Because f of A equals f of B, we have to have a flat line like this. The function's continuous, the function's differentiable, which means that f prime equals 0 somewhere on A to B. So Rolle's theorem is a guarantee. It's a special guarantee that tells you something about when a function will be 0 derivative. Now, you could have many points. Rolle's theorem is what's called an existence theorem. It tells you that you have a point, that this C between A and B exists, but it doesn't say where, and it doesn't say how many. You might have one, you might have a million. You don't know. Rolle's theorem can never tell you how many you have. So for instance, in this situation, you've got infinitely many, uncountably many. In this situation, you've got a continuous differentiable function. There's one, there's one, there's one. You don't know where they are. So maybe you have C1, maybe you have C2, maybe you have C3. You can't find them this way. But nonetheless, Rolle's theorem is good. Math people love existence theorems. They say they love them because it tells you that something is there, and then you can go spend your energy trying to find it. So as an example, let's verify Rolle's theorem for this function f of x is sine squared of x minus cos squared of x on the interval pi by 4 to 3 pi by 4. So this theorem has conditions: continuity, differentiability, and equal value. So is the function continuous on pi over 4 to 3 pi over 4? Okay. F is a difference of trig functions, and each of those trig functions is continuous everywhere. Right? You've got two functions whose domain is all real numbers, hence f is continuous everywhere. Which is good, because then you can shorten that to whatever subinterval you'd like, which tells you that f is continuous on the interval pi by 4 to 3 pi by 4 with square brackets. That's perfect. Second thing, I'm going to jump out of order a little bit. I'll say that f of pi over 4 is sine of pi over 4 squared minus cos of pi over 4 squared. Well, each one of these things has a value of 1 over root 2. They are both positive in quadrant 1. So in this case, f of pi over 4 is 0. And at the same time, if I were to take a look at the sine of 3 pi over 4, they have the same reference angle. It's just that the value of the positive or negative will be different. So sine is positive in quadrant 2, whereas cosine is negative in quadrant 2, but it doesn't matter because they are equal. So yes, indeed, the two endpoints have equal values. So that's another easy one to check. The third one is differentiability. So the only thing you need to do here is actually calculate the derivative. This can be done pretty easily from the chain rule. You'll get 2 sine x times cos x, subtract 2 cos x times negative sine x. So this will end up giving you 4 sine x times cos x. But it's going to make our life easy if we were to write this as 2 times 2 sine x times cos x. And the reason is that this is a trig identity. So we'll get 2 sine of 2x. So the derivative is given by this. It's another trig function. So f prime is a trig function. It exists everywhere. This function has a domain of all real numbers, which means that we can shorten it to whatever subinterval we'd like. And so I'm going to choose to shorten it to pi over 4 to 3 pi over 4. And because of this, my function, the original one, is differentiable on pi over 4 to 3 pi over 4. which means the function satisfies the conditions of Rolle's theorem. And if a function satisfies the conditions of the theorem, that means the conclusion must be true. So we are going to show that there exists a point C somewhere between pi over 4 and 3 pi over 4 where f prime of C equals 0. So how? We just do it. We figured out that f prime was equal to 2 sine of 2x. So we are now going to solve f prime of x equal to 0. So 2 sine of 2x equals 0. Sine of 2x equals 0. Now, students sometimes have trouble solving trig equations like this. Stuff you should have learned about from pre-calc. But when you've got sine of stuff equal to 0, you can think about the graph of a sine function. The graph of a sine function always crosses 0 when this is some integer multiple of pi, so n pi, where n could be positive integers or negative integers. And because of this, you can say that this will be true where 2x is equal to n pi, where n is an integer, and that means that x has to be n pi over 2. The only one on our interval, pi over 4 to 3 pi over 4, is when n is equal to 1 and x is pi over 2. And so we have in fact showed that Rolle's theorem is true. If this function is continuous on the closed interval, differentiable on the open, and the endpoints are the equal height, we have now verified that the conclusion must be true. There must exist a point on that interval where the derivative is 0.